Okay, so welcome everybody to our Elixir meetup. We do this about once every couple of months. I'm joining from Cape Town, but the idea is that it's anyone from South Africa or the broader continent. We sometimes have people join from Lusaka. We've had people from Rwanda and Kenya and so on. So that's anyone is welcome. Today we've got two speakers. I'm very excited to have Danie Palm joining us from LifeQ. LifeQ does embedded devices, medical devices. So from what I understand, it's things like wearables like watches and so on. And it tracks a lot of your health metrics and then gives you insights on those. Danie can correct me if I'm wrong. I'm sure he understands it better than I do. And not everything they do is in Elixir. They do a bunch of C on the embedded side. I know they do other things as well on the server, but it's quite a big team. They're distributed in multiple countries on multiple continents, and in some of those teams they are quite keen on Elixir and they do use it quite a lot. So Danie's working kind of out of their Stellenbosch office, but also mostly remotely. So yeah, without further ado, Danie, if you don't mind, please take it away.
Thanks so much, Petrus. Yeah, so this is as close as I got to working on the hardware. And using Elixir's binary capabilities is also one of those things that I've been looking at for a long time, and everyone is saying that it's so great and cool and you can do lots of stuff with it, but I never really had any use case for it. And so very recently I wrote a parser for the binary data that comes from our watches. We also have, it's a bit of a, what do you call those rituals or right to entry, is writing a parser for the data, because we have one in C, we have one in Python, and yeah, we kind of needed one in Elixir as well. So this is it. It's not gonna blow your mind. Some of it is very basic pattern matching stuff, but we'll see.
Cool. Sounds good.
Yeah, so I guess most of you are familiar with Elixir, otherwise you wouldn't be here, but if not, and maybe anyway, I need to give a bit of an intro to what binaries are. So there are two related concepts in Elixir, the one being bit strings and the other one binaries. So a bit string is quite literally just a sequence of bits. So it's bits strung together, and therefore it's a bit string. It can have an arbitrary length. So it's zeros and ones, and it doesn't matter how long it is. But a special case is if it's divisible by 8, the length, and then it's a special thing that is called a binary. So binaries are then basically sequences of bytes. It's also sequences of bits, but of bytes. And this is how, I don't know if you can see my mouse.
Yeah,
now
we can.
Damn it. Oh, I'm trying to point. Anyway,
That's
so
fine.
this is what a binary looks like. It's, so you use these square brackets, angular brackets, and then you just have a sequence of bytes in there. So binary data is an interesting one, because if you think of most of the other data types that you have, integers, you can think of data types as being on a continuum of data versus presentation. If you think about an integer, 10 is just a 10, right? The value 10 is also how you use it in your code. Maybe if it's more than 1,000, you might introduce the limiter here or there, but integers are pretty close to how you present them. But when it comes to binary data, your language can't really help you that much, because it doesn't know what you want to do with the binary data. Are you interested in bits, nibbles, bytes, chunks of bytes? If you're dealing with multiple bytes, do you use little endian or big endian encoding? Do you want to represent it as integers or floats or characters? And if you do want to present it as integers, do you care about whether it's signed or not? So most languages kind of leave you on your own. They just say, listen, here's a list of bytes. Do with it what you want. And I think in that regard, Elixir is quite nice, because it has quite a bit of syntactic sugar that makes it really nice to work with binary data. So let's look at this string up here and excuse the double quotes. They're supposed to be like just normal quotes, but so this is a string, and I think sometimes it's easy to forget that a string in Elixir is just a binary. So this value up here is exactly equal to this one here on the second line, and the one on the second line is exactly equal to the one on the third line. So you can either represent it as a string, a binary that looks a bit like a string, or as a series of bytes in integer form. And if you really want to, you can also go down to the bit level and you can represent that string as bits. So here I've unpacked the first byte into its individual bits. So it starts with a 0, a 1, a 1, a 1, and so on. And then there's the rest of the binary that I'm not going to write out. So you can.
Sorry to interrupt you quickly. When you're apologizing for the double quotes, you just mean the font, right? They should be double quotes.
No, yeah, it should be double quotes, but
the normal font that we're used to in the editor.
Clever, like going up and down and whatnot. Okay,
cool.
So yeah, but you can give a binary in a number of ways to Elixir. It will convert it, but when it presents it back to you, it will do it in a canonical way, and that canonical way is this line here, with all the integers separated by the comma. And you'll have noticed that I'm using some double colons here. And that is a way to indicate to Elixir what you mean by that 0 or whatever value you have there. And we'll dig into the modifiers a bit later. But just to come back to the canonical form, if you don't give any modifiers, it's equivalent to saying, this is an integer, it's unsigned, it's big endian, it has a size of 8, and it has a unit of 1. So, of course, nobody wants to write all of that, and it's very convenient to work with this canonical form, but nothing stops you from feeding binaries in any form to Elixir, and nothing stops you from matching binaries out again, or matching components out of a binary in using any of these modifiers. So let's look a bit at the modifiers. The first one is binary. So you can say that this data that I've given you is binary. And modifiers are, as I said, it's important when you construct a binary, and it's also important when you match stuff out of a binary. Along with that, you can indicate a size, and you can see that these modifiers are basically separated with a dash. The order doesn't matter. You can put it in any order you want. You can leave some of them out, and then it will just default to whatever the default is. So all of them have slightly different defaults. For binaries, the size is the default size is 1, or actually, I'm not quite sure about that. The unit is 8, but I don't think it has a default size. But anyway, all of them have little nuances like that. But an interesting thing is that you can do math inside these modifiers. So, for instance, in the size modifier, you could say this value that I've given, treat it as an integer of a certain size, and that size you can use arithmetic in there. It's a bit limited. The only math or the only arithmetic or computation that you can do is the same that you can do in a guard. You can't do, for instance, you can't use double ampersands, and you can't use double pipes. So yeah, it's a bit limited what you can do there, but it's all because it goes straight down into low-level C, I guess, when it's executing. And yeah, so we'll see the power of this a bit later on, but it's interesting, you can pass a value that you get from the outside, so it's maybe something that was passed to a function. But you can also put values in here from the same binary match pattern. So if you match multiple things out of the same binary, you can actually use that something that you've matched.
You can use one of those values that you picked out.
Yeah. So that
Okay.
becomes a really, really powerful way of doing parsing. Yeah, so just as I've said, these modifiers are important or useful when you do construction and pattern matching. So let's construct a binary. So let's say I want to start off with the string s. Then I want a float of value 1.2. And now so here I didn't modify the string. If you don't modify a string, the double quotes is modification enough. It basically means it's a binary. Floats, similarly, I've modified here. I said this is a big endian float. I could have left it out because the float part is, you can infer it from the dot being there, and big endian is default, so I could have left it out. Then I put in, just for fun, an integer in hex notation. And I said that must be an unsigned integer. Again, I could have left out the modifiers because those are actually also the defaults. And then finally, I put a character in there. So if you look at what Elixir when it shows this binary that you've constructed to you, it will show it in the canonical form. In this case, the S translates to 115. That float takes up 8 bytes. So it's actually the 63, the 243, the 51, 51, 51, 51, 51, 51. And then you go to get to the hex double F number. That's the 255. And finally, the F character in UTF-8 encoding, the Unicode value for that is 102. So yeah, you can give the binary to Elixir in whatever way you will, and it can make sense of it. Then on the other side, if you want to get information out of a binary, you can use pattern matching. So let's say the binary that I'm getting in here is this 100 and 101 binary. And if I say I want to match that to a binary value, the pattern that I can use is to say bind whatever matches to A and match a 16-bit integer for me. And by the way, 16 is shorthand for size 16. So if you don't want to write out size, you can just write 16. And when I run this, the console gives me back DE. And you say, what? Where does this DE come from? And that is actually because I've been not completely truthful. The canonical form of a binary isn't always an integer like here. Actually, it will try to write a string whenever it can. So when a binary happens to also be, when each element in the binary also happens to be a UTF-8 value, a possible value, it will write out the string. So in this case, it wrote out the string. So matching on the binary doesn't change the binary, but it creates a binding. And so if I print out A, it will give me this 25,701 number. And that is how you do pattern matching and binary construction. Of course, you can list a number of patterns here. You can say, I want to match A, and then I want to match B, and then I want to match C, and A is an integer, and B must be a float, and C must be this literal string value. You can even do things like that. But yeah, let's move on. So this brings me to parsing OTT data. OTT is our internal format. It's short for autobuf, not protobuf. And this is because Otto is Otto Strijdom was the inventor of this binary format.
Cool.
Yeah.
And would this
yes.
type of data running through there, would this then be like data coming from an embedded device?
Yeah, so this is
cool.
Sorry for interrupting you. And this is typically data that flows from a watch. So it will be accelerometer data, and it will be PPG data. So that's photoplethysmography. But it's also data like the data derives from those two streams as well. Like even heart rate is done on the device, and lots of other algorithms run on the device. So the raw data doesn't always make it back to us, but these processed data will. So anyway, ATT, you will often get it in a file, but it was kind of designed to be a stream. So a stream of data comes to you, and it's broken up into frames. And a frame is basically, it's just a chunk of data. Some frames have fixed data, fixed length, and some of them are variable length. And the variable length ones, we use COBS encoding to figure out how long it really is. But the reason that you need frames is that if you're dealing with a streaming data format, you want to do consistency checks, and you might want to be doing compression. But if you do compression on the whole file, it's not a stream anymore. So having frames is a way of doing compression and decompression as a chunk of data comes in. And then you can also verify the consistency with the CRC. So that's a cyclic redundancy check. Okay, but I'm not going to talk about frames and any of that. What I really want to talk about is messages. So each frame is basically a collection of messages. And okay, now I realize my mouse pointer hasn't been where I wanted it to be, but anyway. So what is a message? And so those of you that are somewhat familiar with protobuf might recognize parts of this. It's not entirely protobuf, but it's inspired by it. So we define a lot of different messages. This one in particular is a log event with an error string, and it has a message ID. And then it has 6 fields, each with its own type, and each with a field name on the right-hand side. So a Unix datetime, for instance, takes up 8 bytes. This enumerated type takes up 1 byte. This enumerated type takes up 4 bytes. This one 2 bytes. This is an unsigned integer, it takes up 1 byte, and then a character also takes up 1 byte. This value here in the middle for the enums is basically a namespace. It says what are the possible values that can go into this enum. And then the last one here is a bit interesting. You'll see that it says it's a parameter string of type character, but it's also an array. And the array length comes from the field just before it. So if this thing was packed in binary, there would be 8 bytes from which you need to determine the time, 1 byte for the enum, etc., etc. And then you get to 1 byte that gives you the length of the string that follows it. So this is one of those cases where it would be really handy to, when you need to parse the string, to be able to use the length of it that is given inside the binary. It doesn't come from the outside. You don't know what it is at compile time. Like everything else in this message, you know at compile time, but not the length. Here's another one. It's even more interesting. It also starts off with a datetime, then it starts off, and then it is followed by a period. So both of these are 8 bytes. This period is basically used to determine a frequency. So if it's 1,000 milliseconds, it means the data in this message is 1 Hertz frequency. Then again, there's a data length, an enum type of 2 bytes, and this will basically tell us what kind of data is this. Is this heart rate data? Is this breathing rate? Whatever it is. And then finally, we get to the actual data. And again, we have an array of data, and the length is given in the message itself. But the interesting thing here is that this is a dynamic type. You don't know at compile time what type of data is going to be sent. So in practice, the first byte of the data that you get in that type actually tells you what data you're going to deal with. So here's the first attempt at part of a parser for that last message that we saw. So at compile time, I know everything about, or almost everything about the message. I know that I have to start off parsing a datetime, then I have to go and parse a period, then I parse an unsigned integer, then the enum, and then the dynamic type, which is interesting. Let's just first have a look at this. How would you parse the unsigned integer? And it's actually fairly easy. You tell Elixir, listen, I'm expecting a value. It's an unsigned little integer of 8 bits long. And then you say, it's followed by more stuff that I don't care about right now. And I match my binary on it. And it will extract the value from the binary. And then you return whatever matched, and you can return the rest. And then the rest of your pipeline can extract whatever it needs from rest. But this last one, this parse dynamic type, is a bit different. The first you have to determine the type from the data. So first we parse, we match. There's a bit of a typo here. There needs to be an equals binary here.
Yeah, but then you match in to find the type.
Yeah, so you do a pattern match to find the type ID, and again, it's a unsigned little integer of 8 bits long, and then you have to do a lookup. So what type actually corresponds to this integer value that I've just looked up, and then you have the type, and then you can do some. This is kind of more pseudocode than what I really did, but then you can parse by type. So this one is a bit of a pain. You first have to do some lookups before you can really go on with the parsing. So I wasn't quite satisfied with this because it basically means matching or parsing a message becomes an operation of linear time complexity, because for every field you have to do a pattern match. And actually the worst case scenario is O of 2n, because if you had only dynamic types in a message, you would have to do lookup for everyone, and once you have the lookup, then you do the parsing. So I wanted to see if I can actually, like, most of the data I know at compile time, so why can't I do one big match and grab all of the data in one go? So and if it wasn't for the dynamic types, you could easily do that. And so I had a chat with the engineers, and they said, hey, hang on, the type ID isn't just a random ID that we've chosen. There's actually information in the ID. And it so happens that the first nibble of the ID gives the size of the data in bytes. And the second nibble, so nibble is half a byte. And this is how you grab half a byte in Elixir. You say, listen, I just want 4 bits. Yeah, so you can get the size right out of the ID, and then the second nibble is just kind of for this ambiguation. It doesn't do so much. So armed with this knowledge, I went back to this time I'm going to parse everything in one go from this binary. So I start with a timestamp. I know a timestamp is an integer of 64 bytes. I know time interval, similar but signed. It might actually be a bug. I don't know if it's signed or not. And then I know that it's followed by length, and I know how the length is encoded. Then there's a data tag telling me what kind of data I'm dealing with, and I know how that's encoded. And then we come to the dynamic part, and I now know that I need to parse out the nibble. So I will do an unsigned little integer of 4 bits. That will give me the size, and then I parse out the rest of it as well, and the remaining nibble, and then I get to the actual data. And remember, I said you can do math inside size, and that's exactly what I'm doing here. This is all extremely convoluted, and most people would not, like, usually if you do something like this, it wouldn't look half as bad as this, but I had to deal with a very special edge case, and that was that for 99% of the data, this size
You're breaking up a bit, Danie. But yeah, you're saying there's an edge case, and
isn't, but for the other 1%, the size was
but it
in
doesn't
the
look
first nibble.
that bad either. I think you don't necessarily need to apologize. I think that looks pretty impressive. The fact that you can do everything dynamically just like that in a single match.
Yeah, but the problem actually came in because of that 1% edge case where the nibble says the size is 0, but it's actually half a byte. And then the other part is this rem that needed to be done here, and that is because sometimes you have an array of nibbles, and then it doesn't make up a full. If it's an odd number of nibbles, you don't get to a full byte. So that's why all of that was
the
there.
world is messy.
Yeah, so it could have been much cleaner, and I think it would usually be cleaner, but you can do crazy stuff. Also, these pipes and byte shifting was necessary because you can't use the double ampersand and you can't use the double pipe, and that's why all of this looks so messy. So anyway, what I wanted to get to is the fact that usually when you deal with binary data, you define the structure from the outside, but sometimes some of the structure is inside the message itself, like array lengths and maybe types, like dynamic type data. And Elixir is actually seamlessly allows you to handle both of those kinds of cases. And then the final part. Nobody wants to type this for every message, especially if you have 80 messages. And I mean, it's so easy to make a typo, and if the message changes, you have to recode all of it. So what I did instead was to use metaprogramming for fun. And this is just part of an extract because it wouldn't all fit on the page, but we have a specification, a file that contains all the message specs, and I parsed that with Nimble Parsec. I don't know if you guys know about Nimble Parsec. It's it's a parser combinator thingy. So I parse that spec, and then using the data that I parse, I generate modules during compile time for all of the message types. And yeah, that's basically it. I'm not into skateboarding, but this was part of the template.
Cool. That looks like Venice Beach in Los Angeles. Great talk. Thanks a lot. Any questions? Anybody wants to ask Danie something? Go for it, Nwati.
Yeah, thanks. Thanks for presentation. Pretty interesting. Just wanted to confirm. It sounded like you were saying that like splitting or doing the pattern matching in steps is more expensive than doing it in one go.
Yeah.
Is that true? Because I thought,
it's an interesting one.
The same way as list.
Yeah, so I did some benchmarking on it, and it didn't turn out to be much faster, but it did look like the 99th percentile of the latency was lower. So on average, it was kind of the same thing, but it's like sometimes maybe if you have a very big message, that it would sometimes be slower. But as I said, it's like only the 99th or whatever percentile. So I think in general, it is better to match in one go if you can, but it probably doesn't hurt so much if you do it in steps.
Oh, okay, thanks.
Cool. Thanks a lot for that. Then let's move on to the next talk. We have run a bit over. So if we come to the end of the hour, that's really fine. It was very interesting. But just for anyone, if you have other commitments and stuff, don't feel bad about signing off when you need to sign off. Otherwise, we'll just keep going as long as Wayne needs to keep going. Wayne has a lot of interesting stuff to tell us about. So just to give you a quick intro, he heads up the engineering at Flickswitch. And they're a company here in Greenpoint, South Africa that manages data SIM cards for you at scale. So if you are building some piece of hardware, like maybe a payments terminal or some kind of device that tracks a vehicle or a fleet of trucks or things like that, you need that thing to be connected. You might go to Vodacom and say, please give me 1,000 SIM cards, but then you have to manage all of those SIM cards yourself, and that's quite a hassle. Or you can go to Flickswitch and they can order it all for you from a bunch of different vendors, and you can manage it through their platform. So you can, instead of loading 500 megabytes of data on each of 1,000 SIMs, you can go and buy 5 gigabytes of data and just spread it all across your whole fleet, and they'll manage all of that seamlessly for you. Now, of course, that's incredibly complex behind the scenes because they have to interface with a bunch of different telcos. And if you know anything about telcos, their software sucks normally. The APIs aren't well documented. It's not necessarily stable. And there's lots of different ones. Even one telco across different boundaries, like you could have Vodacom South Africa and Vodacom in a different country, and they might behave differently. So there's a lot of complexity under the scenes. But to do all of that, luckily they've got Elixir. They also use Python in their stack for a lot of the telco-specific integration stuff, as far as I understand. But Wayne can tell us a bit more. So, Wayne, please share your screen and tell us a bit more about Flickswitch. I cannot hear you though, so you might be muted. Sorry. One last thing from me before Wayne starts talking. So he actually gave a talk at ScaleConf, I think it's 4 or 5 years ago, together with the founder of Flickswitch, Kees Snyder. So I'm just going to drop a link to that in the chat if anyone's interested for more of the backstory of how the company came to be and how Wayne joined the company and that kind of stuff.
Yeah, you can hear me now.
Yes, loud and clear.
Okay, cool. Thanks. The intro was great, Petrus, and hopefully we can share something with you guys today. Maybe a bit about our journey and all that sort of stuff, and can have a good conversation. I'm going to keep it quite non-technical for most of it, and then we can maybe deep dive into some other stuff as the questions roll out. But yeah, let's see what we're going to talk about today. So
yeah, just one question before we start. I know you guys don't usually advertise lots of jobs and stuff, but I've got a feeling you're one of those companies that are kind of never hiring, but always hiring and always on the lookout for talent.
Always on the lookout for talent. We hire very, very slowly, and so our team is very small. In fact, most of the team is sitting in the call at the moment because they want to make sure that I don't screw it up. So that's it. But yeah, we hire very slowly, and we hire like very not specific skills, but yeah, there's sort of like a deep understanding of the tech stack, because it takes a long time to get comfortable with what we do. It's pretty niche. So
yeah, cool. But for anyone watching, if this sounds like your type of thing and you're interested, feel free to reach out to the guys afterwards.
Yeah. So like a brief overview of our products and how we started using Elixir, and why we're here. And then I'm going to mainly focus on how we use gen servers and some of the things we've learned along the way, especially like the stupid stuff that we do and we've done before. Some of the quirks and workarounds of using gen servers and like OTP, your apps, and also testing OTP versus like running OTP. It's a bit of a different spot, how that works in real life. And maybe some next steps and learnings. Is anyone using sort of like gen servers here a lot or at scale for stuff, or is it more sort of like using some basic, like using the vanilla Phoenix way of doing stuff? Is anyone like branched out and is using like a lot of gen servers or spawning gen servers and stuff like that?
I have gone that route on a project. I don't know if anyone else wants to chip in.
Okay, cool. So we've got some ideas.
Open. Yeah, deployment open.
Yeah.
Before. Yeah.
Yeah.
The poor man's OBAD.
Also,
Like that, Lucy.
Also, over if you basically a task you with a shotgun that you're going to blow your head off with. So, yeah. So at least we got some people with that sort of stuff. Okay, cool. So our main product is SIM control, as Petra said, and this was originally built in Django and LifeQ and GraphQL. And about 2 years ago, we were like, stuff this, we're going full in on Elixir. We're building another product in that, and the one I'm going to talk about now. And so as of this year, everything is LifeQ in SIM control. And that's across 5 mobile networks across Africa, which are white labeled, and then 4 multi-tenanted sites. This is a big SaaS application, right? So it's got wallets, transactions, billings, decisioning, notifications, everything else that you'd see in a SaaS application. It manages customers' accounts, it manages onboarding, it manages everything it needs to do, interfaces into payment gateways, accounting softwares, export stuff into BigQuery, you know, it does the whole thing. Whatever you expect out of a SaaS product to do, it does that for us and for customers, telco networks across Africa. So we're pretty proud about how fast we did this, and also as a learning from us is like how small the team needs to be with LifeQ to do that. But I'll talk more about that maybe another time. The main thing we're going to talk about is this system called OCS, or Online Charging System. About 5 years ago, we started to integrate more deeply into the network. One of them is ways to do that is by integrating into the packet core with Radius. So if anyone's pretty old or older, they kind of dealt with dial-up modems, and that was Radius, and it was like accounting and authorization protocol that every time you dialed up with your modem, send a Radius request, and that'd log how much time you're online for. Well, not much has changed, and we still use Radius to date, and that's how the networks update us about how much data a SIM is using. And so every 50 seconds, on a good day, we get an update for every single SIM card. So this is about as close to real time as possible. So we knew we were going to handle a lot of updates based on the number of SIM cards we manage. We could do some forecasting and be like, okay, this is going to be a lot of transactions a second. And when we started building this thing, we were like, Python's not going to work for this. So we decided to start building this in Elixir. And one of the design
just to interrupt you here, basically it's a system that pings you with an update every 50 seconds, but you don't necessarily have control over when that update's coming in.
Exactly.
So they could all come at once. They could all.
Exactly. So I'll show you some charts just now, and it just depends on like what type of SIM card is connected to what radio network, what the radio network is doing at that time. Like, so if M10 have an outage in KZN and all the SIM cards come back online at the same time in KZN, suddenly you'll get 25,000 SIMs doing 25,000 requests a second towards you.
Okay.
So
cool.
Yeah, so Radius as a protocol, it's over UDP. It doesn't have any other response, but you can either accept or reject the message. It doesn't have a chill, like, so you can't tell it to back off or anything like that. You got to accept every single packet and respond to it. Otherwise, it's going to resend that packet to you. So if you are not servicing packets, it's going to just keep resending those packets to you. There's basically only 2 packets. It's an auth and an accounting, and that accounting is built into is broken into a start, a stop, and an update. So you can think of it like start your car, cool. Car starts up, and then the accounting is when you start driving. You start driving, and every kilometer it says you've driven a kilometer, 2 kilometers, 3 kilometers. When you stop driving, you've driven 20 kilometers. So OCS is LifeQ and Phoenix and lots of other custom stuff under the hood, and that's made possible by like some base Erlang features like radius and diameter and other baked-in stuff that is baked into like the Erlang Beam VM. So that's where we are with that.
Cool.
Okay, so the first thing we do is like, let's implement some GenServer. So I've got some really shitty OpenAI drawn stuff here because I was under some time pressure today. Don't look at the spelling, but do it. it's all problematic, right? But Petrus will know a bit about OpenAI problems coming up, I guess. So on our system, we probably at about 140, 150,000 active GenServer processes, and about 1,400 requests a second from mobile networks currently. Each of these requests is for a SIM card, and is it on a good day, we'll get an update every 50 seconds. If there's an issue with the SIM card or the network, or with the link between us and the network, we could be getting an update every second for every single SIM card. So we've seen these like dramatic spikes in packets coming our way. And that sort of stuff you just got to eat. Otherwise, if you don't eat it, they just keep coming. So on every single update, you can imagine we have to do real-time accounting. So we debit a bundle of a shared bundle of data for SIM cards, and we calculate the usage, and then we persist the update into the database because that's what sane people do. But maybe the interesting story is like how we started it. So going back to when we started building it, it was basically a single node AWS box with about 10,000 processes. And things were great, right? Every single SIM was a GenServer and was responsible for itself. Kind of was like, I'll do some accounting for myself, it'll update its own state, and then it'll just persist down to the database. And you're doing that, and it's like 150 requests a second. All your naivety in implementing GenServers is still cool, right? Because nothing's really breaking at 150 requests a second. The database access is still good. The inbound stuff is still good. Everything is really, really good at that point. And you're thinking, I've made the best design decision of my life. Yeah, this thing is just going to scale to the sky. So then you scale it a little bit more, and you add some SIMs, and you see that like startup times of your app start going up. And you're wondering yourself, what's going on here? So you carry on going.
Startup time with the GenServer, you're talking about, each SIM is managed by a GenServer, but that goes to sleep and it has to start itself up again when a request comes in.
Oh no! So if you restart the application, so say you deploy the application,
deploy an update or something like that.
Yeah, exactly. And you have to restart the application. You see the startup time of the application is kind of like slow and clunky, and you're like, oh, this is not going so well. But kind of like the CPU redlines a little bit, and then everything sorts itself out. And you're like, cool, I'm good with this. And we had a customer add another 1,000 SIMs to the system, and we decided to deploy like early on a Friday morning, and the application didn't come back up. So now we're sitting there trying to restart the application, and it will just not load anything. I don't know if anyone can guess what's going on at the moment. Well, every single, yeah, go for it.
Yeah,
Lucy, you have an idea? You just
sounds like a thundering head that all these GenServer startup, they all hit the database, then you start getting timeouts. They die, they retry, they hit the database again. So it just the database becomes a bottleneck.
Exactly. And then the database goes really, really quiet after that. So so all these sort of tutorials you read, everyone's like, yeah, GenServers need state, and they give you this thing, and the GenServer starts up with a counter, and then you do the counter thing. And like happy and everyone's pushing counters to each other and all that sort of stuff. But the real meat is like, how do you get real state into a gen server? Right? The main issue also is that at about 300 requests a second, it doesn't matter what you do to your application. If you start to lose any gen servers at scale and they have them cascading failure, you can't actually get them back up, because, as we said, the thundering herd down to the database connection pool at that point is too big. Like, you just will never be able to bring those gen servers back up. You don't. The database connection pool at this point is toast, and there's nothing you can do. So what we did, quick win here, is in the application tree, you write another gen server that starts up, that grabs all your SIM cards, all the state that you need for your gen servers, change the init function of your gen server, and for every single gen server, you start them up manually, and you smash state into them before they start up. So you hand them the state and say, go for it, buddy, you now are live. And then this works well. And you carry on going. But if they still crash, you still need a way to rate limit the access to the database. So at this point, we are working on ways to stop gen servers starting up altogether. So basically what we did is we were like, if we get a request for access to a SIM card, and this gen server is not alive in the process registry, we're going to just send a reject back to the system that's sending us this request, and we're going to put this into a queue and start the gen server up. And hopefully, by the next time they send us another request, the gen server will be alive. And it's really simple, like rate limiter. Things are good. Life's good again, right? Carry on scaling. So that worked well for 30,000 SIMs. Okay.
So that worked well until you had about 30,000 SIMs under your...
From 30,000 to about 50,000 SIMs, right?
Okay. And you're currently at 140.
140, yeah.
Cool. So we still have some...
some stuff
some
to
learnings,
do,
yeah.
Yeah. So I just
Cool.
a little segue about process state, garbage collection performance. So gen server status and gen servers have interesting behavior sometimes, and if you misuse their behavior, it will bite you. So things like process mailbox limits produce very unexpected behavior. So one of our biggest problems in our system is that we have lots of gen servers calling one gen server. We have this concept of shared data. So many SIM cards inside an organization can use one bundle, right? So an organization buys a 100 gig bundle, and 10,000 SIM cards will use that bundle. If you have now you have a thundering herd problem onto the gen server mailbox, and you have to deal with that problem.
Because you have to let all of the SIM cards know at once.
Exactly. Because they can't overuse the bundle, but also if they start crashing, then you have an access problem to your database. So we're dealing with timeouts inside gen servers by adding cache layers to allow us to know when to call the next gen server at the moment, which is a bit of a hack. But that's one thing. Gen servers also are running all the time, and if you do not hibernate the gen server, they are pretty hungry CPU beasts as well, especially when you're running over 50,000 of them. So what we do is after every single GenServer call, we actually hibernate all of our GenServers. So as a GenServer responds to something, we force it into hibernation, because our GenServers only need to process 1 second of work for every 60 seconds of them being alive. We only get an update every 50 seconds, right, from the network. Having a process is a good idea because it's responsible for itself, but for 59 seconds of that whole of its life cycle, it actually does nothing. We also, in some of our GenServer states, we thought it was a good idea to handle things in a list. So we like to know which SIMs are connected, which SIMs are not connected in our life. And one of the things we did is we put a lot of SIMs in a list, and we kept adding and subtracting from this list. So if you want to see Elixir list access behavior RecU at scale, you do this, where you have lots of GenServers calling one GenServer to put something in a list, because the access times will just absolutely destroy you across your all of your GenServer fleet, right? And it's really, really simple. Like something as simple as putting something into a list will kill all your GenServers. I mentioned cascading failure, and it's very hard to, so like this whole concept of you watching Sasha's talk and you say, or you're watching, you know, like a talk and you're saying, okay, cool, this thing in OTP is let fail, it'll restart itself and all that sort of stuff. That's very true. But if you have multiple failures, it's really, really hard to come back from that. So you need to understand the level of failure of your GenServers and how to isolate that failure so that it doesn't affect other GenServers within your system. Does anyone know, for example, if you have a supervised GenServer and it keeps crashing, how many times it will be restarted by default?
My feeling is in infinity.
It's not.
Is it like 5 times?
5 times.
5 times, okay.
So when you're supervising GenServers that are critical and that you think that there might be an issue, you have to actually set the restart count to something like 5,000. Otherwise, the thing is just going to die on you. So if it crashes more than 5 times in a row, it's never going to be restarted. That one the hard way. At 12 o'clock at night.
And then you have to restart the whole application.
Yeah,
but you have to know about it first so that you can restart the whole application.
Right. So you restart the whole application, everything comes online, and then everything would die. And there'd be no, you'd be like, okay,
That sucks.
well, that sucks.
Hang on, wouldn't the, sorry to interrupt, but wouldn't the supervisor crash after 5 times itself? I think there's something like that where the supervisor would then crash, and then that can crash 5 times before its supervisor crashes, and you go up the whole hierarchy. It's something like that. I don't remember.
I think you're right, Donnie. But it might also take down the other child processes in the supervisor as well.
Yeah.
Something like that.
Yeah, it will.
But I didn't know. Yeah, so it did break us. Okay. Then garbage collection in GenServers is notoriously fickle. If you store anything over 64 bytes inside a GenServer state of binary objects, it won't get garbage collected. So we, like Donnie was talking about bit strings, we have this nice location bit string that we like to see where the SIM is located. So we thought that was a good idea to store that in the GenServer state of our GenServers. And every time a SIM moves from one tower to another, this bit string gets updated, right? But the GenServer never gets garbage collected. So suddenly we're dealing with 32 gigs of process state inside our applications, and we were wondering why this doesn't get garbage collected. So what you need to do is make sure that when you're running GenServers is have enough state that is viably possible for you to run the GenServer, and that's about it. If you keep adding more stuff into the state, it's going to break eventually. You can call Hibernate to do the full garbage collection as well, but it doesn't work after. Stefan, just give me a heads up here. It's after 64 bytes,
so
right? It doesn't get garbage
we were
collected.
storing a substring of a binary that was larger than 64 bytes. So it never, because it was reference counted, it just never got cleared up, even though we were only storing a small little string.
But is this because you're still hanging on to a reference to it in the state of the gen server, or?
Yeah, exactly.
No,
So
Okay.
yeah, I think we solved that with the binary copy thing, but that never gets cleaned up, even if you hibernate or force a garbage collect.
I think there's another case for big binaries. They actually don't get copied between processes because they're so big. And so then all the processes reference the same binary, and then you start to get...
Then it doesn't get garbage collected because there's still a reference dangling somewhere.
Yeah, and also if it maxes out the reference counter, it just returns bigger than 0, and then the garbage collector can never come along and do it because it doesn't know when it was last referenced. Yeah.
Okay. Cool.
We're learning that. So we're chugging along about 50,000 sims, and then we decide to make our system HA. So in the Radius protocol, you can it allows you to do 2 nodes, and the 2 nodes are in active state. So the
HA here being high availability for those who are wondering.
Yeah.
So you have a failover.
Exactly, but they're both active. And what we did is we linked the 2 nodes up, and we talked, a lib cluster between them. That was easy. That's 3 minutes worth of work, and then the 3 months of pain starts straight after that. All right. So we have 50,000 processes sitting on one box, and we have another box, and that doesn't have any processes on it. And now you're paying for 2 boxes, and only one of them has any processes on it, which is great. That's fine. Okay. But then the first box goes down with all the processes on it, and now you're back to the stampeding herd problem that you had when you had startup, because you have a global process registry and it can't find those processes, and now it's trying to start up those processes again on a different machine because all of the processes have gone away. The main problem with this is that you sometimes need to cache data for access outside the gen server. So we tried a few different caches, like Nebulux and CacheX and things like that, to store some, like, not gen server type of data, but more like tariffing and data from the database in the application. And the one thing that is problematic with distributed Erlang is that everything seems to want to have consistency over availability. So anytime you have a distributed cache or implementation in Erlang or in Elixir, like Nebulux or CacheX, it has to have a global lock across all the nodes to write. So just to start up the application and for the cache to be hydrated, the startup time for the application went from like a couple of seconds to over 20 minutes, just trying to write into the thing.
Shucks.
Yeah. So we had to reverse that, and we were starting to think about, okay, how's this going to work? We have an its cache, and we have just like a really basic like its layer here, and we just do gets and sets into its, and we have a pub sub running between the 2 nodes, and we broadcast updates between the 2 nodes between the its caches, just to keep things semi in sync. It's not the most consistent way to do stuff, but it is the fastest way to keep data in sync between the 2 nodes. Yeah, so if node 2 is getting written to at the moment, and cache updates in its are happening, it just broadcasts via pub sub, and there's a gen server listening on node 1, and that updates the its cache in node 1. And that's good enough for now. So that's a way to get around this whole like distributed cache lock nightmare. So one thing we also learned is that moving to a distributed Erlang type of environment, your gen servers need a global process registry. And this is great because it'll ensure that only one node is running one version of the process, or only one process, as per the name. What really sucks is that this also needs a global lock to start this thing. So to start like 50,000 gen servers, 60,000 gen servers, it takes a while, right? But you've got these back-off mechanisms that you put in place based around the database, and it kind of works. So like you restart the thing, and 5 months later, all your processes are up. After 100,000 processes, there's no way that you're starting anything with a global process, with the global process registry. There's absolutely no way.
After 100,000, you say?
Yeah, after 100,000,
Okay.
there's no way. You'll be sitting there for 30 minutes trying to get these things to start. So what we found is we had to use a third-party process registry, SIN, that allows us to start up the processes very, very fast, and actually uses PubSub to broadcast the updates between its two process registries on each node and keep everything in sync. So it's not guaranteed, but at least we can start up the process registry in 30 seconds, all the processes in 30 seconds compared to over 30 minutes if we're using a global process registry.
So am I correct that that's then going to be eventually consistent?
Eventually consistent, yeah. So what we'll see on a restart is that we'll see that like node 2 will go down, and some processes will migrate into node 1 because they'll get updates. Node 2 will come back up and try to restart processes, and there'll be some inconsistency, and then like in about 30 seconds everything is sorted out, where the processes die and all that sort of stuff. So that's that.
Okay.
We did mask the whole process registry problem for a long time with the whole backing off the process starting and things like and pre-starting processes as well. So that took us a long time to figure out. And there was a lot of like frustrated nights trying to restart application servers, waiting for the thing to come up. So that was some dumb shit.
I'm glad you learned the hard way so you can pass on some of the knowledge to the rest of us.
Cool. So let's talk about breaking the database's rights. So what's the worst thing you can do with a gen server is probably write to a database. At the same time, I said that in the beginning, right? Everyone's poor man's task you. Well, not really. This thing just breaks databases left, right, and center. So what happened with us is that we realized we had a problem. We started spawning off like tasks, so we don't want to write to a database within the gen server, because if the database pool is not there, it breaks the gen server, and then the gen server restarts, and then you can't. Then the gen server can't restart because it doesn't have access to the database pool. So we're like splitting those writes off in tasks. We're just doing task async, and that was working well up to about 50,000 gen servers. And we're writing. So we write like updates, like how much the SIM is used back down to the database and update the SIM. But after that, it was like, okay, this is getting a bit hot, like the CPU and the amount of sessions on the database. So we plugged Broadway in there, and we were like, cool, we'll use Broadway. And what we did was we were rate limiting the inbound writes onto Broadway with some concurrency stuff. So we'd use like 8 workers or 8 processes and just do individual writes into the database. And this worked really, really well up until basically January this year. And we had to change something because we'd gone from 110,000 SIMs to 140,000 SIMs at that point. And you could see stuff was like really, really creaking at this point. So like, we have to change this. So what we did is we actually contacted Lars. I don't know if you guys read some of his stuff. And we got him on board to just do like a quick code review of our system, and just like an optimization review. It's like, cool, what can we what could we get you to show us or help us focus on to optimize in the next 2 weeks? And that was a really, really quick engagement. And one of them was changing from single writing updates in Broadway to batch writing. And it sounds like really stupidly obvious now once you say it. That's what we should have done first of all. But sometimes when you're just trying to keep things running, like that's not what you see. And there was some complexity in the way that the previous context modules were written that didn't allow us to do that. So we actually had to rewrite some of the context modules. So we rolled out some batch writing, and the first time we rolled it out, after testing it and all that sort of stuff, we hit production, and it basically blew up. So everything blew up in production. The batch writes were slower than the individual writes, and we were sitting there, the team, and we were going, well, what the hell's just gone on? And the stupidest thing in the world is that if you do an upsert with certain columns, like a date time that is indexed, the update will be slower than an individual write. So this is what we only learned as we were doing this. Yeah, I'll show you some stats here about.
Sorry, is this just because the index had to be updated for each record? So even if it's a batch insert, you still, and there are 100 records now, 100 new records need to be put in the index somewhere, and that's not necessarily done smartly.
I think that's my understanding. Louis, maybe do you have a better understanding of that?
Yeah, I need to re-look up.
You did at one point.
We did remove the indexes, but I don't remember if that was the main thing that put all the speed up.
Okay. So this is like February the 22nd, when you can see this is the average active session count inside the database. And once you start batching stuff, you can see what happens, right? So it dramatically improves your performance. But this is the blocking duration when we had the session inserted at time here. So it was taking us 12 seconds to write that each individual bulk upsert. So figure out that was pretty.
That's quite long.
Yeah, that's a long problem. And this is a screenshot from today from one of our processing queues. You can see how many messages we're doing in the last hour. So we did 8.5 million messages in the last hour, 36,000 batches. And so we try and batch every 500 milliseconds, I think, or 400 milliseconds. And our batch throughput is under 10 milliseconds now. So taking it down from, I think it was about 75 milliseconds a write to under 10 milliseconds on the throughput, but the processing time is what, 240? Yeah, milliseconds on the batch throughput. So what I'd say is, when you're dealing with gen servers and writes, you have to do something like this from the get-go. You have to have like a strategy where you say, okay, cool, if I have a lot of gen servers and I'm writing to the database, I have to build something like a throughput pipeline that will help me handle the load. Otherwise, you're going to be in a whole lot of trouble. Cool. Testing. So everyone, if you've used a gen server before, you've done some of the stuff like assert received, and you've made sure that the gen server works in isolation. Was one of our biggest problems. Our gen servers all worked in isolation and correctness, but it was very hard for us to get something where we were able to mimic what real life load was on our system. So Ross, who's actually not here today, who lives in the UK, wrote our first version. And the most simplest thing that we could do is we took a live book, and we took the seeds file, and we built a database seeder that could seed in 1 million SIM cards into our database. And then we used Livebook as a client, and we smash the hell out of our system when we need to. And we don't actually look at failures because we know that there's going to be failures. But what we do is we monitor the system with Prometheus and like open telemetry at that point, and see whether we are in band of performance, acceptable performance of the system compared to of production. So we look at like performance bands and say, okay, cool. Have the changes we made been able to do this, been good for the system or bad for the system, right? And that's how we kind of know how the system will perform in production. There's no other real way to test, to put that amount of load on the system that allows us to do that. Right? So using some tools that are there, like Livebook. Okay, and what's next? So part of our journey with Lars is we started to plan out what we're going to do, and some ideas from like Stefan and all that sort of stuff. So we might decouple our GenServer architecture and try and get rid of some of them, because it's a liability trying to run that many of them all the time. So we're thinking of moving a lot of the code to revolve around like just its values inside its, and having access into the its value, and then making a decision at that point, and then having the process move on and doing something else. We need to investigate dynamic rebalancing of processes across nodes. So at the moment, if the process is skewed to one node, there's very little way for us to move a portion of the processes over to another node. So we have a skew of where our processes are running. And then we also need to work on load balancing requests into the GenServer. So at the moment, they all come in via like a UB port and then an Erlang call into like an RPC call to a GenServer across the cluster. So we need to figure out a better way to load balance the inbound requests to go to the correct server where the GenServer that it is at wants to needs to talk to. So we have some ideas about that. And then also memory optimization. So every single time we make a change, we have to make sure we're optimizing memory and make sure that we're not doing dumb shit like that. So it's like a constant sort of pull towards making things better inside the code base. So yeah, that's it. The very high level stuff about how we're using GenServers and some of the stuff we learned. We're happy to answer some questions.
Cool. Thanks for that. I think it was very interesting. Any questions from anyone that's not me?
First question. It's less of an Elixir question. Where does the data live? Does the client own the data once you guys have processed it, or is it just like it sits on your side, then they kind of view that data and they extract it for other business processes?
So what we do is, this is just like our online charging system. So it does aggregation and the billing. And then our SIM control product actually does the reporting and analysis. And a lot of stuff I left out is that we built a WebSocket connection between these two systems. They live in two different data centers across the world. And so SIM control knows about what SIMs are in this OCS system and then can push. And then OCS also pushes updates in real time into SIM control, so that the customer has a full view of what's going on in their SIM all the time. So it's the data is the customer's to use, but the customer doesn't understand the data at this point. It needs to be aggregated even further inside the SIM control application to make them understand what's going on. That makes sense?
Cool. Anyone else? Any comments or questions? I'll go for it, Danie. Danie, you are muted.
Ah, damn it. What a rookie. Anyway.
Happens to the best of us.
I was wondering if you're using consistent hashing in any way to help you place a Gen server on a node, and if you think that could help.
We are not using consistent hashing yet. We are going to use consistent hashing, like with libring, I think from Bitwalker. There's like consistent hashing stuff there that we're investigating. Honestly, we would have done like this dynamic rebalancing stuff, but the network changes stuff all the time, and there's just so much stuff to react to. Like at the moment, M10 are sending us duplicate sessions from 2 different packet gateways across their network because they had an outage. So we're getting double the amount of traffic that we have. So we have to deal with that. So it's like, yeah, that the consistent hashing will become a thing, and like the node, the process placement will become a thing in the next like 3 to 4 weeks, I guess, for us. So that's like definitely on our radar. But yeah, thanks for that. It's a good thing.
Cool. Thanks.
Anyone else? Any comments or questions? Cool. Now then, let's wrap it up there. I want to thank you for that insightful talk, Wayne. I know it's quite complicated stuff, this, so it's difficult to just quickly summarize and transfer all of that information to us so quickly. So thanks for taking the time to do the slides. It helped a lot. I found the talk very insightful myself. And thanks for Danie as well for the first talk. That was much more interesting than I anticipated, to be honest, just from the title. Yeah, cool. So thanks a lot for joining, and then see you again in a couple of months or so when we do the next one. We might do another in-person one, probably around Joburg next, but then also a remote one before too long. Cool. Cheerio. Keep well.
Cheers up.
Cool.
Cheers.
Cheers. Thanks, guys.